Hi everyone, Mr. Boltri here bringing you video 5.7. We're going to be talking about rotational work and power. So first we're going to review what we already know about work, then talk about rotational work. Then same thing for power, reviewing and then talking about rotational power. So first, let's remember everything that we've already learned about work. So first, we've said that work is just a change in energy. Work into the system causes more energy in the system, or energy can leave the system via work. So to calculate work, we said that we have to find the force through the displacement. That's kind of how it's defined, is force through the displacement. You get newtons times meters. Newton meters is a joule. A joule is energy. Energy is work. But the important thing here, the reason why we have to multiply by this cosine theta is because it's only the force that's in the direction of that displacement. If there is a force up and to the right, and then an object is moving to the right, then we only want the right component of that force to figure out the work in that direction. So this is typically the work of any individual force, and then we can add all of those works together to get the net work. But if we don't want to multiply by this cosine theta business, there's also another thing that we can do using vectors, which is the dot product, which gives us the same thing. This is just the force in the direction of that displacement, which is what this force cosine theta is trying to do. And then integrate all those forces, and then we get the work. So then when we add all those works together, we get the net work. And by the net work kinetic energy theorem, we can see that the net work equals the change in kinetic energy. And we've had a lot of kind of trouble wrapping our brains around this, and it's only because that the network is all of the forces acting on it, and so that's going to include some conservative forces and some non-conservative forces. So that's why the network kinetic energy theorem is a little bit different from our definition just of straight up work, is because the network kinetic energy theorem incorporates some conservative forces and some non-conservative forces. So this is everything we already know about work. If you need a review, you can definitely go back and rewatch the work video. But now let's talk about rotational work. So rotational work, as you're probably noticing the pattern, is going to work basically the exact same way. But we're going to think about it just a little bit differently, because instead of moving in a nice straight line like we were before, we are obviously now moving in circles and curves and rotations. So we have to think about it just a little bit differently. So the way that we're going to think about this is we're going to think about just a little bit of work at a time. So just a little bit of work at a time is going to be, we're going to figure that out by the same way, by doing a force through the displacement, but this is going to be rotational force or torque through the rotational displacement or angle theta. So if I just go a little, if there's a little angle theta and we figure out the torque working through that little angle theta, that's going to give us a little amount of work. And so if I want to find the total amount of work, then I can just integrate all of these little thetas from, if I want to find the work done from angle A to angle B, theta A and theta B, I can just integrate from those two angles, theta A to theta B, of all the little amounts of work. So what that's going to look like is, since the little amounts of work can be found by the formula of the net torque through the angular displacement, I can just say that the work from A to B is basically the net torque through the angular displacement as evaluated from theta A to theta B. So you'll notice that this is very similar to our definition for regular work, which is basically just force through a displacement. That's kind of the most important thing you have to remember, is that work is the integral of force through a displacement. And so then the other thing that we can do here, if we know the work done from A to B, theta A to theta B, and this is going to be using the net torque. So this is the net work done from A to B. And we know by the network kinetic energy theorem, the net work is going to equal the change in kinetic energy. So then we can say that the work done from A to B equals how much the kinetic energy changed from A to B. B minus A is the delta kinetic energy. And since here we're talking about rotational work and we're using torques and angular displacements, we should also use the angular kinetic energy, 1/2 times the angular mass, moment of inertia, times the rotational velocity squared, or angular velocity squared. And then, so the really cool thing about this is, well, it's probably an eye roll for you guys, because it means that AP can ask some really hard questions where you're having to evaluate this and then set it equal to this. That's kind of a big hint of the kind of questions that they like to ask with these rotational work problems. But again, sort of highlighting the fact that this is basically nothing new. The work is the force through displacement. It's just angular force through an angular displacement. And then the network kinetic energy theorem also works if we say the net rotational work equals the change in net rotational energy, kinetic energy, excuse me. So now, again, we're just sort of reviewing and then applying it to rotational stuff. But let's review what we know about power. We said power is the rate at which work is done. So therefore, power is the derivative of work with respect to time. I guess the rate with respect to time that the work is done. So since work, linear work is a force through a displacement, linear force through a linear displacement, we can just take the derivative of that with respect to time. And if we're lucky, then the force is going to be constant with respect to time. And then so we can just pop it out. And then the derivative of the displacement with respect to time is just velocity. Now, if force is not constant with respect to time, then we'd have to do like a whole chain rule thing here, and it would be a pain in the butt. But we know how to do chain rules, so that's not actually that product rule, excuse me. We could do a product rule here, which isn't that bad. But if force is constant, which would be nice and lucky, then we can just use this very easy formula of the force dot product with the velocity. So we're going to see a very similar thing with rotational power, because it's still the derivative of work with respect to time. But now rotational power is the derivative, obviously, of rotational work with respect to time. So the rotational work is basically just tau times theta, because it's force through a displacement, tau theta. So again, if tau, the torque, the rotational force, is constant with respect to time, we can pop it out of this derivative, and we can say that the torque equals the derivative of the angular displacement with respect to time. Now, again, if tau is not constant, we can do a product rule, and we're good at that. But if the torque is constant, the rotational force is constant, and the derivative of the angular displacement with respect to time is just the angular velocity. So this is kind of the lucky case of if torque is constant, and then we can just do the calculation a lot more easily. But if it's not, we can do a product rule on this derivative, because we are able to do stuff like that. So this is the rotational power formula. And so now, just as a quick summary, again, just trying to show you the parallels, is that what we're learning, we're applying it in a new context, and rotational can be kind of tricky, kind of hard, but it's kind of nothing new except the new context that we're applying these theories to. So work is force through displacement, and if we want to find the net work, it's going to be the net force through the displacement. And again, so the work is going to be the net torque. This is the net work from A to B is going to be the torque, the angular force through the angular displacement from theta A to theta B. So, and the same thing with power. Power is the derivative of the force times the displacement. Angular power is the derivative with respect to time of angular force through an angular displacement, which if force is constant, we get lucky, and we can just say the force times the velocity, angular force, torque, times the angular velocity. So we're going to do some practice problems with this in our next class, but for now, this is Mr. Boltri wrapping up video 5.7 on rotational work and power, and go Bears.